Hello everyone, welcome to the video lecture of gas vapor mixture and air conditioning. Today we are going to talk about basic definitions of all the air properties, and then eventually we'll start talk about the air conditioning system. So let's start with the gas vapor mixture. What is the meaning of the gas vapor mixture? So basically in the TS diagram we discussed previously that if you have this saturation dome, right? Just to give you an example, if you have the saturation dome, then this region is considered as a superheated region. Superheated. This is the gas vapor mixture, right? uh, Liquid vapor mixture or gas liquid vapor mixture, liquid vapor mixture, and this is completely liquid, right? Or liquid, and this is the critical point, right, from where the liquid is started to become the vapor. So here in this chapter it starts with the gas vapor mixture, right? So what is the gas vapor mixture actually? So the gas vapor mixture, gas vapor mixture, so the gas vapor mixture is nothing but, first of all, the vapor implies a gaseous state, right, that is close to the saturation region of the substance. Now if we, there is a if we basically decrease the temperature of the vapor, we will see that condensation happens, right? Due to the condensation due to the condensation it becomes liquid, right? So or it condense, or that vapor is basically converted to the high moisture content, right? So it happens when we decrease the temperature below the critical temperature. So in this case the gas mixture is referred as a two-phase mixture. So if we see that a vapor is basically decreasing due to the decreasing temperature, it becoming condensate, right, and converting to the liquid, then we call it a two-phase mixture, which is the water vapor mixture. So then it becomes two-phase mixture, right? So imagine right here, if we have for example this TS diagram, if we see that basically if we this is our constant pressure line, right? However, if we decrease the temperature here, we saw that this was the gas phase and it's becoming the liquid vapor, because we are basically decreasing the temperature. So if we decrease the temperature, it's converted to the two phase two-phase mixture, right? So basically it becomes two-phase mixture. So in most commonly used gas vapor mixture is most commonly used gas vapor mixture is air water vapor mixture, right? So again, in summary, gas vapor mixture is nothing but the mixture of air and water. When we decrease the temperature, it becomes condensate. Okay, now let's define the dry air and atmospheric air, right? So what is the dry air and what is the atmospheric air? So basically dry air, there is no water vapor. There is no water vapor in the air. This is called the dry air. right? So there is no water vapor. However, the atmospheric air, in the atmospheric air, basically it is it is a mixture of the, like, water vapor. So in the air in the atmosphere, air in the atmosphere normally contains the water vapor, right? So basically it's referred as the atmospheric air. So in the dry air means that there is no water, right? In the atmospheric air there is a mixture of water vapor. So basically in the atmospheric air, if we, like, atmospheric air or atmospheric pressure, the definition would be like total pressure would be that pressure of the air plus pressure of the water vapor, right? So this is air and this is vapor, right? Pressure of the water vapor. And also we can define that the enthalpy of the water vapor in the atmosphere is basically enthalpy of water vapor it's basically 2500.9 plus 1.82 times absolute, uh, uh, actually this is in Celsius, degree Celsius, right? So this is one thing we have to remember, that whenever we need to determine the enthalpy of the water vapor, at like certain temperature, then the enthalpy the relationship between the enthalpy and temperature would be this. Okay. Next thing would be that now we know the air properties. So basically in the air, sometimes we see that it could contain, like, vapor, and then we define that, if there is no vapor then it's called dry air. If there is a vapor in the air then we call it atmospheric air, right? Now let's define that what if certain percentage or certain amount of air is presented in the certain percentage of the vapor is presented in the air, then what they how we can define them. So one of the definition is that specific humidity. I'm pretty sure everybody is familiar with this one. Specific humidity, or we call it absolute humidity, or we call it humidity ratio, right? So basically we express it through the omega. So what is the definition of this one, or what is the meaning of this specific humidity and is or absolute humidity, or humidity ratio? That's what we are going to take a look, right? So basically the amount of water vapor, excuse me, the amount of water vapor in the air basically is known as a specific humidity, or basically the humidity, absolute humidity. So basically if we define this, if a specific humidity omega, then mass of water vapor divided by mass of dry air. So amount of water vapor in the dry air, dry air is known as the specific humidity. So it's nothing but the ratio of water vapor, ratio of the mass of water vapor, ratio of mass of water vapor by the mass of dry air, right? So that's the basically we express it this ratio in kg uh, per kg. So kg of water vapor per kg of dry air. Okay, so that's the definition of the specific humidity or humidity ratio, right? So there is another definition which is called the relative humidity. So there is another definition, relative relative humidity. Relative humidity is nothing but the ratio of the ratio of the water vapor ratio of the water vapor ratio of the moisture in the air to the maximum amount of moisture maximum amount of moisture the air can hold at the same temperature, at the same so how basically we define this relative humidity by phi. So phi is nothing but the mass of water vapor, right, divided by the mass of the maximum amount of water vapor that can be held within that and dry or within that air, right? So basically that's the definition, or that's the expression of the relative humidity. So if we express it with the ideal gas, right, so the ideal gas relationship, we can write the p pressure of the water vapor times the volume divided by RT, right, divided by the pressure of the maximum moisture content in the air times volume divided by RT. So this will be omitted, right? So it will be relative humidity definition we can write in pressure of the vapor divided by pressure of the maximum vapor can be presented in the air, so Pg, right? So in terms of humidity or humidity, we can write this or specific humidity, the relation between phi and omega. Basically relative humidity and specific humidity is like this. We can write it this way: omega times pressure divided by 0.622 plus omega times Pg. So we will use this relationship for the math problem, and the omega will be 0.622 times Pg times phi, and divided by P minus phi of Pg. Here the P is the pressure of the atmospheric pressure, which is the summation of the air pressure and the moisture pressure or the vapor pressure. Okay, so This relationship will use them for the math problem, right? So I would like to define like couple more definition, and then I think we'll be done with this definition. So another definition is the dew point temperature. So dew point temperature. So dew point temperature, we know, everybody knows about the dew, right? So basically in the morning we see in the grass the dew droplet. Dew point temperature is nothing but if you have like um so dew point temperature is nothing but like for a constant, you know, if you have you know, the constant pressure line, and then you basically decreasing the temperature, and you know, decreasing the temperature, at some point you will see that it started to becoming the liquid, right? So vapor, right, or the gas, and then this is basically the liquid, right? So you are decreasing the temperature along this line. So the dew point is nothing but the, it is defined as, it is defined as the temperature at which the condensation begins. Condensation begins when the air is cooled at constant pressure. At constant pressure. So here this is a constant pressure line, right? So we are basically decreasing the temperature, and then, you know, although it seems like the constant pressure as well as the constant temperature line, you know, we are basically decreasing the temperature from here to here, then we see that it is started to becoming the liquid, right? So the dew point temperature is defined that one. So dew point temperature is nothing but the saturation temperature at which it started to becoming the liquid, right? So we'll define a couple more definition, and then I think we'll be done for the basic definition of this chapter. So another definition is that adiabatic saturation or wide bulb temperature. So basically adiabatic saturation, so adiabatic saturation temperature. So one of the ways of determining the relative humidity and humidity ratio is like, you know, the dew point temperature. The basic relationship is that T dew point temperature is greater than the pressure of the vapor, and which is also very very, you know, greater than the omega, or like specific humidity, or the relative humidity, right? So how we can determine that specific humidity, or relative humidity? So another way to determine these two parameter is that adiabatic saturation temperature, right? So what is that adiabatic saturation temperature? So a steady steam or stream of unsaturated air that has specific humidity omega 1, let's consider a steady stream of unsaturated air, unsaturated air that has a specific humidity, which is omega 1, right? And the temperature T1, right, is passed through this channel. through the channel, right? Then what happens that when the airflow over this water, right, for example, right, so this is omega 1 and T1, and then the airflow is happening on top of this one, or over this channel, right? So what is happening, airflow stream, right? What is happening is basically some of the water evaporates, right? Some of the water basically from this one evaporates this channel, right? And then it get mixed with this airflow, right? So this moisture content of the air is basically the increasing, right? So increasing the moisture content, increasing the moisture content. So increasing the moisture content, and its temperature is decreasing, right? Why? It's because a part of the latent heat of vaporization of the water that evaporates comes from the air. So so again, if we have like a stream, let's say consider this is the open channel, right? Let me remove this line. So if we have this stream, so basically this is water, right? This is water flow having through this stream, and then the air is flowing over this stream, right? Now basically this water is taking the latent heat of vaporization, latent heat of vaporization, right? Absorbing that latent heat of vaporization and becoming the vapor, and that vapor is basically like is mixing with this airflow, right? So if the channel, like sufficient enough, or the long enough, the air stream exists as a like the saturated air. Why? It's basically it's converting all those water into the water vapor and mixing with this the airflow, right? So that means that humidity becomes like 100%, right? 100 percent at that temperature. Let's say when the water is mixing with, or the vapor is mixing with the air, temperature is decreasing, right? So latent heat, by taking the latent heat of vaporization, temperature is, it's basically decreasing, and that temperature is nothing but the T2, right? So this T2 is known as the adiabatic saturation temperature. So if we define that, first step is that water is absorbing the latent heat of vaporization, from the air, right? And then the relative humidity becomes, or sorry, the specific humidity becomes is it no, it will be relative humidity. Relative humidity becomes 100%, right? And then also the moisture temperature decreases. The moisture temperature decreases, right? And that temperature is nothing but T2. So this temperature, decreased temperature, is known as the adiabatic saturation temperature. Adiabatic saturation temperature. Okay, so if I ask you to define the adiabatic saturation temperature, it is nothing but the when the water is basically absorbs the latent heat of vaporization, the temperature of that vapor decreases, right? And where the vapor it's completely converted to the or this water vapor is completely converted to the vapor and the relative humidity increases up to 100%, right, the temperature decreases of that moisture content. So that moisture content temperature is called as or known as the adiabatic saturation temperature. Okay, so we have one more definition. Basically adiabatic saturation temperature, we have one more definition which is called the wet bulb temperature, right? So wet bulb temperature, wet bulb temperature. So wet bulb temperature is nothing but a temperature. So for example, if we have a like a thermometer, right, okay, so this is the, if we have a thermometer, then we can determine like the temperature in several ways, right? One of the way would be that this we can like just like leave it like as it is, right? So then we can get the temperature, right? So this is basically the dry air temperature or atmospheric air temperature, right? However, if we cover up this thermometer with a white like cloth or whatever it is, right, some sort of like white wipes, right, then it will measure a different temperature. It will measure that most basically that the white temperature, right? So it's basically if we cover with the cotton wick, right, like which is the saturated with water, saturated with water, then it will measure a temperature. That temperature is basically known as the white bulb temperature, right? And so if we blow the air, right, uh, air, right, so basically it will get this, we will get this white bulb temperature. So we need to have this white bulb temperature to compare like or to get the specific humidity and relative humidity data, enthalpy data um, from psychrometric chart. So we'll talk about the psychrometric chart in upcoming lecture. So that's all about today's class. So we just defined some basic definition, right? We'll come back with the new topic psychometric chart and we'll go ahead and solve math problems. So thanks for watching this video. We'll come back with another video.